Hello. Good day to everyone online. My name is John Barker. I'm a solutions architect with NVIDIA based in Washington, D.C. Today I'm going to talk about the deep learning framework Theano. This is the fourth class in our Introduction to Deep Learning online course. We'll begin today with a introduction to what is Theano and where does it fit into the deep learning ecosystem. We'll cover a simple first application that's kind of a model, a recipe for how all applications are written in Theano. Then we will move on to the specifics of Theano for deep learning and a more complex example, and some related projects and examples. So the first thing I think it's probably important to say about Theano, the deep learning framework, is that Theano isn't really specifically a deep learning framework. It's far broader than that. It's actually a Python library for symbolic maths developed by the University of Montreal. It allows you to define almost any algorithm in a symbolic mathematical form and then compile that into Python functions that can operate on numerical data. It's tightly integrated with the Python ecosystem. You'll see that the syntax of Theano is a lot like NumPy, the Python numerical matrix library, and it has a very fast C and CUDA backend, so that when functions are compiled from their symbolic representation into functions that can be applied to numerical data, this is done transparently for different computational architectures, in particular CPU and GPU, and then you can get the benefits of running on those different architectures. So what do I mean, to make it a little clearer, what do I mean by a symbolic maths library or symbolic expression compiler? So rather than requiring that variables are defined with numeric data associated with them from the start, instead, in Theano, you define your variables like you would in algebra. You give them a letter or a name. They're a symbolic representation. So here we see an example where we have a vector called X, a matrix called W, and another vector called B. And then you can define symbolic expressions using these variables, but with a syntax that is very familiar if you know NumPy. So here we show that we can do the dot product of the vector X and the matrix W, and then apply a sigmoid activation function to the output of that dot product summed with the B vector. So at this point, before going on, I will say, although this is an introductory course and an introduction to Theano, there is quite a lot of code in this presentation. It's unavoidable because Theano is a Python library, but it's not critical that you're able to understand every detail in that code. Hopefully, I'll be able to guide you through what the code is achieving, and then when you do the hands-on lab yourself, you'll be able to look at it in more detail and actually experiment with the code yourself. So before we go on, just a couple of additional notes about Theano at a high level. It's very mature. It's been developed and in use since January of 2008, as I said, created at University of Montreal. Now has a large contributor community. It also does have tools for inspecting and debugging code. The error messages that Theano produces are different to standard Python error messages, so these tools can be helpful in understanding the root cause when those error messages are produced. And a resource that I use a great deal, not only when I'm using Theano, but for understanding deep learning algorithms more generally, are the tutorials and examples provided by the deep learning developers at the URLs shown on this chart. So in addition, so Theano actually gives you three things in the Python library. There's a language, so that is a syntax for defining these symbolic variables, these symbolic expressions and functions built from those expressions. There's a compiler which will take those symbolic expressions and variables, compile them into code that can be run on the CPU or GPU. And then there is a library of functions that you can use within the language that make it easier and more concise to define symbolic expressions. So for example, if you're building a convolutional neural network, there's a convolution function, and if you're building any neural network, there are various activation functions that you can call upon from the library. So the basic recipe for building any application in Theano. Oh, my slide just changed, sorry. The basic application for recipe for building any application in Theano is that you define your symbolic expressions, the variables and expressions. You then compile a function that can compute numeric values using those expressions. Then you apply that function to data. So we'll start with a very simple example, but this is indicative of even the most complex neural networks. So you will start in your Python program with importing Theano as you would any other library. A convention that's often used is that we import the tensor submodule from Theano as the letter capital T. So in a lot of Theano tutorials, you'll see that done. We then initialize symbolic variables. So if you were writing a Python program normally, you might see a equals and then some numeric value. In this case, all we're doing is telling Theano that a is going to be a scalar, so a real number, and b is going to be a scalar. You can also define your symbolic variables to be vectors or matrices, as we showed before, or actually even much higher dimensional tensors, and I'll come on to that shortly. So in this example, our application is going to attempt to compute the product of these two scalar values, a and b, and output the value y. So we define our symbolic expression using our symbolic variables a and b, and then y automatically inherits its type as another scalar from the fact that a and b are defined as scalars. But at the moment, we have no way of actually giving numeric values for a and b and finding out what y is. So this is where we have to compile a Python function using the Theano.function method that defines what the inputs are to the function and what the outputs are, and then Theano automatically uses the symbolic expressions to work out how you compute y from given values of a and b, and then we can apply that function to numeric values that we provide. So nothing I talked about there is specific to deep learning. That was purely a symbolic maths and compilation example. So why is Theano so widely used for deep learning? Has a number of useful features that we'll talk about in detail. So as I mentioned, this symbolic computation, symbolic variables and symbolic expressions are not just for scalars, vectors, or matrices, but indeed for multidimensional tensors. So here, a tensor, it's a word that's used in different contexts for different meanings. What we're loosely referring to here is any n-dimensional matrix. So for example, if you're building a convolutional neural network, the bank of filters that you're going to convolve your input images with are often represented as a three-dimensional tensor, a three-dimensional array, and then when you apply those over a batch of images, the feature maps, the activations, becomes a large four-dimensional array. So tensors crop up all over the place in deep learning, and all of the symbolic computation that Theano provides can be applied to tensors. Similarly, I mentioned there are libraries of functions that can be applied to the symbolic variables in Theano. Many of these functions are tensor operations that are specifically relevant to deep learning, such as convolutions or activation, neuron activation functions. Theano is highly expressive. Really, if you want to add a new activation function or a new loss function, it's just the same as defining any other Python function as long as you conform to the Theano syntax. So the sky's the limit in terms of the network architectures you can build, the training algorithms you can use within Theano. And as I mentioned, you get this benefit that Theano is integrated within the Python ecosystem. So it's very easy to build Theano applications into larger Python data analytics applications. But at the same time, Theano compiles down to efficient C and CUDA code, so you get high-speed computation and the ability to transparently leverage GPU acceleration. So I'm just going to dive into a few of those important topics in more detail and also explain what I mean by this symbolic differentiation, which is an important feature of Theano. So to give an explicit example of where tensors or matrices crop up in deep learning and how Theano allows you to define functions upon those. We have here a very simple artificial neural network on the left. So we've got 3 neurons whose output values are x1, x2, and x3. We've got 2 more neurons whose output values are y1 and y2, and the x neurons are fully connected to the y neurons, and they have these weights on the connections. So if we want to compute what is the output activation of y1, it becomes this sum of products of 3 of the weight values along with the output values of x1, x2, and x3, and then we apply this sigmoid activation function. Similarly for y2, it's a similar sum of products but with different weights. So this can actually be written, this pair of nonlinear equations can be written as a nonlinear matrix equation, y bar equals sigmoid of w x bar, where x bar is just the vector x1, x2, x3, y bar is the vector y1, y2, and w contains all of the weight values. So in Theano, we can define w and x symbolically, and then we can define this feed-forward operation where we pass the activations from the x layer to the y layer using tensor functions provided by Theano. So if you have a mathematical background, or even more generally, this is a very natural way to express deep learning architectures and algorithms and then tie those to efficient computation. As I mentioned, it's very easy to add new activation or loss functions. It's much like adding any other Python function. So here I have an example of adding a leaky rectified linear activation function. That's just a neuron activation function that is x times 0.01 for x less than 0 or x otherwise. And this Theano.tensor.switch function applies that activation, and it's actually can apply to element-wise to tensors. So the x input here can actually be a whole array of neuron activations. Similarly, we can easily add new loss functions. Here we see the cross-entropy loss being added again, much like adding any other Python function. One of the really useful and important features of Theano for deep learning, I'll try and explain on this one chart, is this symbolic differentiation. If you recall from our very first introduction to deep learning class, we had this very simplified picture of supervised training of deep neural networks, where we have a large amount of labeled training data going into a deep neural network, which attempts to make classifications of the training data, and then we pass back the errors in those classifications to update the weights in the neural network so that it will do better next time it sees an image that it made an error on. So I didn't give any more detail in that first class about how this process of passing back the errors to update the weights actually work. The way that works is that the function to update the weights is actually a function of the partial derivative of the error with respect to the parameters. It turns out if you formulate a deep neural network mathematically, it's non-trivial to work out the partial derivative of the output error with respect to all of the parameters, especially as you go down to the lower layers of the network. It can be quite complex to do that analytically using pen and paper calculus. Thankfully, Theano provides automatic differentiation for symbolic expressions. So here at the bottom we see we are calling our error our cost in Theano syntax. So our cost is this value L. We want to differentiate it with respect to W, which might be one of the weight matrices that defines the links between one layer of the network and another. And all we have to do is invoke this t.grad function to get that partial derivative back as this gradient variable. And then we can apply that an update to our weight matrix W using that derived gradient. So this greatly simplifies implementing complex neural network architectures and adding new loss functions when you don't necessarily know how to analytically derive the gradient. Okay. So moving on to a slightly more complex example of how you would apply Theano in a machine learning context. This example is still not a deep learning context. In fact, this is just going to be a simple fitting a line of best fit, if you like, to a scatter plot of data. So we're going to try and fit a linear model to the blue scatter plot of data you see here. The Python code on the right shows how this data was generated. So it's effectively a linearly spaced set of data in the x-axis, and then it's the function y equals 2x with random Gaussian noise added to get the y value. So we want to hopefully learn the scalar value w, this real value, so learn that that value should be 2, y equals 2x from this data. And there's a credit at the bottom of the slide to where this example comes from, and a deeper tutorial on Theano, which you may want to look at, that uses a similar example. So to implement our linear model, we first need to initialize symbolic variables as before. So we need a variable for x and a variable for y, and these are scalars. We then define our symbolic expression for computing y. In this case, we actually define that as a Python function itself. And then at the next step, we initialize this W model parameter. So what you see here is a new term, this Theano.shared. These are actually hybrid variables in Theano. So I mentioned that symbolic variables don't need to have any data associated with them when they're initialized. Shared variables do have data associated with them, but they can also be used in symbolic expressions. So that's how you have hybrid values. So it's typically used for defining model parameters, which are going to be learned through some machine learning process. We then define our model using the model Python function to give us this y equals x times w. It's a machine learning use case, supervised learning, so we need a cost function that tells us the error on a model prediction given the ground truth. So in this case, we define that symbolically again. Then we define the gradients that we will need to update the parameters of the network. So as I showed before, this is the derivative of the cost function with respect to this weight w, which is just a single value. And then we define how we would like to update the weight in using that gradient. So I believe I just saw a question come through on the chat about how is backpropagation implemented in Theano. This is how backpropagation is implemented in Theano. You define your cost, you define gradients, you define how to update your parameters based on those gradients. You then have to define a function that will compile these symbolic expressions down to efficient C or CUDA code. Again, we have to define our inputs and our outputs, but this time we also tell it what symbolic expression to use to update our parameters each time this function is invoked. And this final term you see, this allow input downcast equals true, just to so that's not left a mystery. This is in there because if you want to use GPU acceleration, you need all of your floating point values in Theano to be 32-bit floating point values. But by default, if you defined your values in the way I have shown here, or if Python by default may define your parameters with 64-bit floating point values, so this takes care of that difference when the function is compiled. And then finally, we just iterate over our data set. So this was train X for, and train Y for the coordinates of our data points. We do that 100 times. Each time we invoke this Theano function, and every time we do that, the cost is calculated based on our current value for W and the training data X and Y, and then we make an update to that W value to reduce that cost function next time we see that same piece of data. And what we find is that before training, I showed that we randomly initialized W to have the value, let me just go back to that, to have the value 0. That was what was happening here. W was random initialized to 0. So that corresponds to a straight line, y equals 0x. After 100 iterations, W has become very close to 2, and we have a good line of fit for the data. So again, everything I just described, that machine learning example, is completely indicative of how you would define a more complex machine learning use case where you're using stochastic gradient descent to train a deep neural network. Really, the only added complexity is how you keep your code efficient whilst defining some of these much more complex layer types and symbolic expressions, such as a convolutional layer. So here on this chart, I've got an example of how a convolutional layer might be defined as a Python class. Again, it's not important to understand all the code here, but what you're seeing is that we would give the class an initialization method that would take some input data. It would randomly initialize W here, the convolutional filters that are going to be applied to the input data. It would then apply the convolutional operation using that value of W you've initialized. It would then apply a nonlinear activation, in this case a hyperbolic tangent function, and we specify which parameters of this layer are going to be trainable, and in this case it's just going to be our W value. So that's how you might define a convolutional layer as a Python class. So then to define a deep neural network architecture, you simply stack instances of these Python classes where the output of one class, of one instance becomes the input to the next. So here we see 2 convolutional layers. We pass in parameters that specify the filter sizes and the input data size. And in the first case, in the case of layer 0, which would be the first layer, we pass in this layer 0 input, but then when we get to the second layer, layer 1, which is also a convolutional layer, the input there is actually the output of the first convolutional layer. And that's really how you define any more complex deep learning architecture in Theano. Okay. So as you will have seen, Theano is very expressive. You can very easily define much more complex architectures, loss functions, activation functions, training algorithms. Along with that expressiveness, though, comes a quite complex code in some cases. If you instead want to build some of the very standard neural network architectures and apply them to a data set, much like you did with Caffe in the last lab, there are other libraries that have been built on top of Theano which do take care of things like defining these Python classes for convolutional layers, and instead they just provide those as methods or as functions in these libraries themselves. So some popular ones shown here are blocks, keras, and lasagna. These are all machine learning algorithms that are shown on this chart here. And as I say, the objective of them is typically to simplify the syntax and the interface for artificial neural network training, but at the slight expense of expressiveness. So I have an example next of how you might define a convolutional neural network using keras. I've not chosen keras for any specific reason. This isn't a statement that we recommend it over any of those other libraries built on top of Theano. This is just one example, and I recommend you look at those other libraries and projects too. Most of them, I believe actually all of the ones listed there, are open source projects. So if we were defining a convolutional neural network with an input layer and then a convolutional layer with max pooling, and then a fully connected or dense layer with dropout regularization, and then another dense layer doing our final classification, in keras we can define that in the around 20 lines of code shown on this chart. We import a number of the keras submodules, which provide the particular functions we will need for defining this architecture. And then in the same way as I described before, the layers of the architecture are simply instances of functions from the keras library chained together with the output from one being the input to the next. But what keras has done is taking care of defining those classes for you. And then you can also specify the parameters of your training algorithm quite simply. Here we choose that we're going to train with stochastic gradient descent with some actual modifications such as Nesterov acceleration and momentum. We define our loss function, and then actually training the model is a single line. So as you see, much more concise than doing this yourself in raw Theano, but at the cost of some expressiveness. So I want to move on to a few examples now of where Theano has been applied to different problems. Actually, both of these examples both slides of examples I have are from the same researcher called Sander Dielman, who works at Google DeepMind in London and is also a PhD student at the University of Ghent. He was previously an intern at Spotify, and whilst there he used Theano to develop a convolutional neural network approach for taking music audio as input, representing that as if it was an image by representing it as what's called a Mel spectrogram, so a time frequency representation. And then at the output, computing latent factors or tags that might be applied to that music to describe it, so that when you have a collection of those latent factors or tags, you can find similar music, do similarity-based search on different songs. So Theano allowed him to take a convolutional neural network and apply it to this non-standard data type very easily. And there's a great blog post on this work at the URL shown on this chart. So Theano was also used by the same researcher in 2 Kaggle contests. If you're familiar with Kaggle, these are online data science contests, and it was actually used to win both of these contests. One, this little picture on the left shows a number of data samples from one contest, which was to classify the type of galaxies from a radio astronomy data set. And the other challenge was to classify the type of plankton from underwater imaging data. The reason I put both of these examples up was, again, it was the easy extensibility and expressiveness of Theano that allowed Sander to very easily come up with new and creative data augmentation strategies that proved to be, and weight sharing strategies for the network that proved to be critical in winning these competitions. What I mean there is data augmentation are modifications you make to your data as it's ingested into the network so that the network better generalizes as you train it. And weight sharing is a way of reducing the number of parameters you need to train in your network and providing better translation invariance in your detector. So Theano really enabled the easy addition of those functions. Finally, I mentioned earlier, finally for the examples, I mentioned earlier the very good tutorials and examples provided by the deep learning, by the Theano developers. They start at very simple examples, similar to some of the ones we have in the hands-on lab, so linear regression and multi-layer perceptrons, but they go right through to some of the most cutting-edge recurrent neural network formulations and work being done on unsupervised learning. Both of these, again, are very easily enabled by the expressiveness of Theano. To do unsupervised training, you can quite easily specify that your loss function takes as input the output from the top layer of your neural network, but also the original input data in what's called an autoencoder formulation. And if you want to define recurrent neural networks, you can easily define that some of your networks in your layer receive their last state as input at the next state. So there are some great examples of Theano being applied in those use cases. So what does it take to run Theano? Theano will run on many distributions of Linux. I didn't list them all here. Certainly Ubuntu, Fedora, CentOS, Red Hat Enterprise Linux. You can find a complete list on the Theano website. It will run on Mac OS X and it will run on Windows. The requirements are Python greater than 2.6, the G++ compiler, and NumPy and SciPy Python libraries, and then a BLAS library. Theano is very easy to install. The most basic instructions, if you want to use the current stable release, is either use pip to install Theano or easy install. If you want to get some of the bleeding edge installs with developmental features, you can clone the Theano source from GitHub, and there's a Python setup script to install it. When you install Theano, you'll want to configure it. There are 3 ways that you can pass configuration parameters into Theano. One is you can define a .theano.rc file. This is just a text file that lists a set of parameters such as do you want to use GPU or CPU. This is typically where you'll set settings that you always want every time you use Theano. So, for example, setting that you want to run it on the GPU. If you want to choose a setting for just one job, then when you actually invoke Theano, so you do Python on you run the Python command against a script that's going to use Theano, then you can pass in different Theano flags at that runtime, or you can actually make changes to the configuration in the middle of your Theano code using the theano.config submodule. To leverage GPU acceleration, there are three ways that you can add the device equals GPU flag to the .theano RC file. You can pass in a Theano flag device equals GPU when you invoke your script, or you can set that, use the theano.config submodule and set the device is GPU in your code. And if you have cuDNN installed as part of your CUDA installation, including version 3, then Theano will automatically pick up that that is there and use that to accelerate some of the deep learning tensor operations. So that's all the slides I was going to cover in today's webinar. I'll move on to questions now and then come back to close up with the schedule and hands-on lab at the end. So one question is, does Theano have to be compiled with support from the GPU at compilation time? If you have CUDA installed, when you install Theano, then when you compile a Theano function based on the Theano.rc configuration I mentioned before, the GPU will be used, but there's nothing different that you need to do in terms of Theano installation, assuming you have a working CUDA installation to get GPU support within Theano. So what class of GPUs are minimally required for Theano? Any CUDA-enabled GPU basically will be able to use Theano. If you want to try out a GPU instance and you don't have one on your local machine, you could use Amazon or SoftLayer, both offer cloud instances with GPUs that are capable of running Theano. Or if you have a GeForce home gaming card, that would work great as well. Another question was, what exactly is activation in the context of neural network structure? So an example of an activation function is the sigmoid function I mentioned earlier. So shown here for a very simple artificial neural network, we applied, after we did the sum of products of the weights and the X neuron values, we applied the sigmoid activation function. Activation functions are nonlinear functions that you apply to the sum products that form artificial neurons. And the reason we do this is that if we stacked together many layers of artificial neurons and we didn't have a nonlinear function in that layer, we would only actually be able to still learn a linear function by the larger stacked neural networks. So we have to introduce nonlinearities so that we can learn more complex nonlinear functions that map our raw data to outputs. So you don't have to use the same activation across your whole network. You can have different activations on each layer of your network. The sigmoid is, if you like, the traditional activation function, and it's just really a function that takes arbitrary real-valued numbers and squashes them into the range 0 to 1. In very modern neural networks, it's fallen a little bit out of favor. People now more typically use what are called rectified linear activations, especially in convolutional neural networks, which is where you take the sum of products of your neuron inputs and weights, and then you take the maximum value of 0 or that sum of products. Or people often use hyperbolic tangent function as a nonlinear activation function. Another question was, how is this related to autoencoders? So activation functions are used on the layers of a neural network that is in an autoencoder, but there's no unique relationship between activation functions and autoencoders the relationship is the same as between activation functions and any other type of neural network. In an autoencoder, what is different is that you are not training your network in a supervised training fashion where you have labeled training data. Instead, you're training your neural network so that the error is computed by comparing the output of the network to the original input. So to give a specific example of that, you can train an autoencoder on images to attempt to produce a dimensionality reduced feature vector that describes the image. So maybe you have 256 by 256 pixel images, and you would like to have 10-dimensional vectors that describe them so that you can do quick similarity-based search on the images. Well, in an autoencoder, you would take the 10-dimensional vector learned by the network. You would then upsample that to produce a reconstructed image, and your error would be the comparison of the original input image and that reconstructed image. How can we create LSTMs with Theano? LSTMs are long short-term memory networks. They're one of the popular recurrent neural network types that are being applied in natural language processing, arguably the most popular type at the moment. There is actually a great Theano tutorial on the website I mentioned before. If you go to the deeplearning.net/tutorial/lstm.html, then you can see an example of doing exactly that. So there's a number of questions about the advantages of using Theano for deep learning compared to Caffe. So the philosophy of Theano is slightly different. It's not, as I mentioned earlier on, it's not a deep learning framework per se. Caffe very much is specifically aimed at deep learning, and today largely aimed at training convolutional neural networks on image data, although you can do more, as we saw last time. Theano is much more general than that. It's the symbolic maths library with compiler, so you can define. It's much more expressive than Caffe in defining algorithms, but not necessarily neural network training algorithms. But the flip side to that expressiveness is that it can be harder to get into, harder to learn initially. But some of the libraries built on top of Theano certainly help that if you're trying to get into Theano specifically for deep learning. Can Theano be executed without GPUs? Yep, that's a great question. Yep, absolutely it can. You can pass this device flag in with set to CPU, and you can execute on CPU, but it will, for deep learning applications, it will be much slower. One question is, what Python editor do I use? It's Sublime Text 2. Oh, a great question here. I mentioned earlier that when you're doing deep learning applications, you have to use 32-bit floating point values. Again, the three methods I mentioned for configuring any of the parameters in Theano can be used. So just flip to that slide. In the .theano RC file, you can specify you specify the parameter float x to be float 32, but you can also do so passing it in at runtime or mid-code for a settings change. Is Theano compatible with Ubuntu 15.04 or any other Linux distributions? Yeah, as mentioned, it works on many Linux distributions, also Windows and Mac, and even you can compile it on the Jetson TK1 if you would like to run Theano on an embedded GPU. So I mentioned that there were tools for inspecting and debugging Theano code, and the question said, I've heard Theano is hard to debug because of symbolic declaration. Theano can be somewhat complex sometimes to trace back Theano errors through what's called the computation graph. So that is the sequence of symbolic expressions that are being applied to computer answer and trace the root error. But there is a debug mode. You simply add another one of these Theano flags or configurations options called debug mode to the code, and this can provide more verbose explanation of where in the computational graph errors have occurred, but you should be aware that you don't want to run in debug mode all the time because it actually will slow down your Theano code somewhat. Someone asked, is the best way to use Theano with Anaconda Python? I like using Anaconda Python. It tends to be a pretty hassle-free way of getting all of the dependencies and libraries that you would commonly want to use in conjunction with Theano, but it's certainly not necessary for running Theano. So what does it mean when a shared variable is initialized to borrow equals true? I think I showed this earlier. Oh, I didn't show this on this chart. So here we have that W is a Theano shared variable. So I mentioned that that's a hybrid variable. It can be used in symbolic expressions, but also has a numeric value. What borrowed equals true does, it prevents multiple copies of the data being, the numeric data being created in memory effectively. So when you define, for example, a Theano shared parameter with borrowed equals true, and you compile your function to GPU, that the value will be copied over to GPU and it won't be duplicated or copied over multiple times. So what out-of-the-box solution does Theano have against vanishing, exploding gradients and deep architectures? Well, so Theano doesn't offer an out-of-the-box solution to that problem. Really, none of the networks do. None of the deep learning frameworks do. Instead, but you can very easily define recurrent neural networks, and many of the modifications that have been introduced over the last few years in the research literature, such as gated neurons, that do help to deal with the vanishing and exploding gradient problem. So again, yeah, that's a great example of where Theano is massively expressive. You can certainly get the latest research paper with a method for dealing with exploding or vanishing gradients, and you can implement that in Theano, but you would need to do that work yourself. So here's a great question, actually coming back to the comparison between Caffe and Theano. How do they deal with large data sets? Large images, and I would kind of extend this question to really how is data managed in Theano generally. Because if you did the hands-on lab and the webinar last couple of weeks ago on Caffe, you will have seen Caffe offers a large number of tools to help you manage data. You are kind of shielded from the data structures that are being used in the back end for efficient application of deep neural networks to the data. So Theano doesn't provide that same level of data management functionality. And again, it's an example of the trade-off of expressiveness versus ease of use. You can use any method you like in Python to manage your data, to pass your data into Theano functions, to save your Theano models. As I mentioned, Theano models are essentially a set of Python classes and a Python function. So any way that you might normally back up an instance of a Python class, such as a pickle in a pickle file, you can use within Theano as well. There's no specific difference between Theano and Caffe for handling large data. I mean, it really boils down to the data processing pipeline and the infrastructure and resources you have in your Python environment for handling large data. Does Theano support other languages? I don't believe so. I believe all of the Python interfaces and the libraries I mentioned before are also, sorry, Theano libraries extensions I mentioned before are also Python. What is the difference between MATLAB and Theano other than programming language? Again, it's that MATLAB is closer to NumPy. MATLAB is a numerical matrix language. At heart, Theano is a symbolic maths language. That's the fundamental difference. How is using Theano.function different from calling the same function defined separately multiple times? That's a great question. Theano.function, when you call that, it's not just saying define a Python function if you use the usual Python def, as we see on this chart here, def model xw. Theano.function is actually telling Theano to define this function using the previously defined symbolic variables and compile that down to efficient code for application to numeric data on the architecture. So you're not just defining a Python function, you're actually telling Theano to compile a function on the underlying CPU or GPU that can be run efficiently on the underlying CPU or GPU hardware. Just coming back. Most of the examples, people say most of the examples they see are for image or audio recognition or time series prediction, and we've seen that Caffe is more suited for images. What frameworks and algorithms are suited for classification on time series data from sensors? Well, Theano, you could certainly do time series classification on sensors. Again, as I mentioned, really the sky's the limit for the types of data you can ingest and the architectures you can build and train. But there are other frameworks specifically for other applications. So for example, if you're doing audio, you may want to go speech recognition, you may want to look at the Caldi framework, and you'll hear about Torch in the next class, which can also has a similar level of expressiveness for different applications. But specifically for time series data from sensors, I think Theano would be a fine choice to start with. How does one use Theano with multiple GPUs? That's a great question. It's similarly, there's currently, as far as I'm aware, no direct parallelization for deep learning applications across multiple GPUs, whether it be the data parallelism or the model parallelism approaches, but certainly you could implement that in Theano yourself. I will actually revisit that question at the Q&A next week, because I have to admit I'm not 100% sure of the current state of multi-GPU usage in Theano. Can Theano be used for natural language processing? Yep, absolutely. In fact, Theano is great and popular for natural language processing because of its tight integration in the Python ecosystem. Python is very powerful for string manipulation and has associated libraries that can do useful things like tokenization of text data, and so those can be very easily integrated with Theano. And as I mentioned earlier, really the most popular current approach for natural language processing in the deep learning context are these long short-term memory networks, a type of recurrent network, and there's examples of those being implemented in Theano. Just sifting through the questions here. Are there publicly available example implementations of common deep learning elements, or do you have to start from scratch? Absolutely, there are examples at the deeplearning.net/tutorial URL I showed before, so I would recommend not starting from scratch. Similarly, if you're going to use one of the common deep learning approaches that have been well demonstrated, like convolutional neural networks for image classification, I would recommend looking at the libraries such as Keras and Lasagna that I mentioned before. But when you're learning Theano, I would recommend starting out looking at something like those tutorials of how the common elements are implemented as Python classes in Theano, because Theano is what's called a functional programming language. If you've not programmed in this way before, it may take a little bit of adjustment. There is a bit of a learning curve. So those examples are a great way of helping you understand the Theano syntax and process. So one question, quite a deep question here about Theano is how to use Theano's scan function for recurrent neural networks. We can't really answer that. It's not really a one-line answer. Scan is basically an efficient way of doing loops in Theano. How you would use that well, one answer is it's not really specifically closely tied to recurrent neural networks, so I recommend understanding the scan more generally, but we would have to discuss a lot of recurrent neural network theory to really explain that. Are there references for compiling Theano on the Jetson TK1? Because I mentioned that. It's exactly the same as compiling on any other Linux, any other installation. You can just do pip install Theano and you're done. Okay. Are there examples of Theano being used for regression, so prediction of continuous numerical data, ideally time series? So the simple linear model example I showed is a regression. We're computing this value W, which is a continuous value. Again, I recommend the same tutorials, in particular the recurrent neural network tutorial on the deeplearning.net website touches on time series prediction. Okay, and I think I've got time for one more question. Just find an unanswered one. Great question here. Are there some converters from cafe models to Theano, Lasagna, or Keras libraries on top of Theano? Yes, there are. I don't have a reference for one off the top of my head, but there certainly are a couple of open source examples on GitHub of of people converting Caffe models into Theano models. I would say, I mean, that's a somewhat complex thing to do. The easy part is getting the Caffe model. Julie just provided an example in chat. The easy part is getting the Caffe model out into Python, but actually structuring a deep neural network in Theano that can make use of that model is quite a complex proposition. Okay, so I will just finish up here and move on to mention that next week, same time, we will have the office hours for this class. I'll revisit a couple of those the questions, such as multi-GPU in Theano, and take any other questions you have, either about this webinar, the course in general, or the hands-on lab. And then 1 week after that, my colleague Alison Lowndes from the UK will be giving a Getting Started with the Torch Framework webinar. The hands-on lab for this, associated with this webinar, is live now at the bit.ly address shown on this chart. As always, all you require is a browser, no GPU required on your part. We'll provide the GPU, and the lab will be free till the end of this series. So thank you once again for participating today, and look forward to answering some more of your questions next week.